Okay, good morning, all of you. Am I audible?
Yes, ma'am. Audible.
Okay, so yesterday we have solved one numerical on shear force diagram and bending moment diagram. Okay, so yesterday we have solved simply supported beam with central point load. Okay, and today we will discuss some points regarding shear force diagram and bending moment diagram in simply supported beam. Okay, so my screen is visible. Yes. Okay, so once again I will draw figure here and then I will explain some points you have to remember for the examination point of view. So this is our simply supported beam and one central point load is applied on that beam. Okay, so I will draw shear force and bending moment diagram and then I will explain. W is applied, this is A support, this is B support. This distance is L by 2 and this distance is L by 2. So I will extend first lines, then we will solve problem. So shear force at A point. The value of shear force is W by 2. Here again W by 2. Okay. Here minus W by 2. Here minus W by 2 and here 0. Here 0. This diagram is in positive and this diagram is in negative. Okay. So here this whole diagram is in positive and bending moment value is how much? W
Upon 4.
L by 4. W L by 4, na? W L by 4. So bending moment at A which is equal to 0 and bending moment at B which is equal to 0. So this is the bending moment diagram and this first one is the shear force diagram. Now we have to write some conclusions from this shear force and bending moment diagram. So first I will write and then I will explain. Okay. So please write down first, then I will explain. Write down first conclusion from these figures.
मॅम 1 मिनिट ड्रॉ करायचं.
Okay. Okay. So our first observation from this shear force diagram. Okay. So shear force in case of point load. Okay. You observe here shear force in case of point load connected by horizontal lines. बघा A point पासून आपण C point पर्यंत A point चा shear force आणि C point चा shear force हा आपण कशी कुठल्या लाईननी कनेक्ट केलेला आहे? तर shear force has been connected by horizontal straight line and shear force remains constant between two locations. You observe here shear force from A to C is constant. Then from C to B is constant. That means whenever we will draw shear force diagram in case of point load, this diagram will be connected by horizontal straight line and shear force remains constant between 2 points. So this is the observation number 1. Then we will write second observation. You can also write. So second observation is maximum shear force which is equal to maximum shear force which is equal to how much? W by 2. Maximum shear force which is equal to W by 2. Okay, maximum shear force which is equal to W by 2. Okay, but you remember this W by 2 value for simply supported beam, simply supported beam with point load at center, So this value will comes when if simply supported beam is given and on that in that simply supported beam central point load is applied. At that time maximum shear force which is equal to W by 2. So for this observation definitely one question will be asked. The maximum shear force value for simply supported beam with central point load is W by 2 minus W by 2, WL by 4, WL square by 2. So you remember if simply supported beam is given and central point load is applied, at that time maximum shear force which is equal to W by 2. Okay, so this is our second observation. Then we will write third observation. In case of point load, connection between two bending moment values, two bending moment values is inclined straight line, Okay, you observe here. So this is our bending moment diagram. Okay, so whenever we will draw bending moment diagram, if centrally point load is applied or if point load is applied, either it may be center or it may be some distance. So whenever we will draw bending moment diagram for point load, at that time connection between 2 points is inclined straight line. Okay, and here x raised to power is 1. That's why here inclined line will be come. Okay, here x raised to power is 1. That's why inclined straight line is there. Okay, and last assumption number 4. Write down last assumption. Maximum bending moment which is equal to WL by 4. Maximum bending moment which is equal to WL by 4. Okay, WL by 4 for which type of beam? Simply supported beam simply supported beam with central point load, with central point load, with central point load. Okay, with central point load. And last assumption you have to remember, this is must, that is assumption number 5. Shear force value becomes shear force value becomes 0. Shear force value becomes 0 at that point, at that point, at that point, at that point. Now you tell me, okay, you observe here, here shear force is 0. Shear force is 0. At that point, the value of which value is maximum? बघा, ज्या पॉइंटला शियर फोर्स 0 आहे त्या पॉइंटला कशाची तर व्हॅल्यू जास्त मिळते. कशाची येते हो जास्त व्हॅल्यू? बघा बरं. You observe here shear force is 0. At that point, the value of bending moment is maximum. You observe here, the shear force is 0 at C point and maximum bending value at C point. And shear force is maximum at A point and bending moment value is 0 at A point. Okay, so you have to remember, where shear force is 0, at that point bending moment value is maximum. So this is most important assumption. Shear force value becomes 0 at that point, you will get maximum bending moment in the beam, maximum bending moment in the beam. So once again I will repeat all observations. So from this shear force diagram, we observed that the shear force diagram in case of point load, okay, shear force diagram in case of point load connected horizontally straight line between 2 points, okay, between 2 points, and shear force remains constant between 2 locations. After that, maximum shear force, which is equal to W by 2. Maximum shear force is W by 2 when simply supported beam is given and in that central point load is applied. After that, from this bending moment diagram, in case of point load, bending moment diagram will be connected by inclined straight line, and here x raised to power 1. So this 1 indicates line is inclined straight line. And maximum bending moment for this simply supported beam with central point load is applied. So maximum bending moment is WL by 4. And last assumption, shear force is 0 at that point, bending moment value is maximum. So on these 5 observations, definitely 1 or 2 MCQ will be asked. So please write down fast. Then we will solve next problem. Okay, your writing is over or you want time?
Ma'am.
Okay. So we will take next example, that is simply supported beam with UDL. Simply supported beam with UDL. Shear force and bending moment diagram. Please write down. Shear force diagram and bending moment diagram for simply supported beam, simply supported beam for simply supported beam with UDL throughout span, UDL throughout span. That means simply supported beam is given, and on that beam, uniformly distributed load is applied. Okay, uniformly distributed load is applied. So first I will draw figure, then we will solve problem. So suppose this is simply supported beam AB. Okay, and here central point load is applied. Here central point load is applied. Sorry, uniformly distributed load is applied. So this is uniformly distributed load is applied. W kilonewton per meter. Okay, and the length of this beam is L. Length of this beam is L. So we have to calculate shear force values, bending moment values, and then draw shear force diagram and bending moment diagram for this particular case. So whenever we will start solving problem, at that time our step number first is reaction calculation. So first we have to calculate reactions, reaction calculations. So whenever we will calculate reactions, at that time first we have to take summation of vertical forces, which is equal to 0, and while taking addition of vertical forces, at that time upward force will positive and downward force we will consider negative. So accordingly you tell me summation FV, which is equal to, how we will consider, RA plus RB. Okay, because of this RA and RB going upward direction. So RA plus RB, and this W kilonewton per meter force going downward direction. So minus W into, this is uniformly distributed load. So we have to multiply by L. So L, which is equal to 0. W into L, which is equal to 0. Therefore, RA plus RB, which is equal to WL. So this is our equation 1. After that, second equation. Which equation is there? Second equation, summation movement at any point which is equal to 0. Okay, now whenever we will take movement, clockwise movement will be plus and anti-clockwise movement will be minus or negative. But these sign conventions are only useful for reaction calculations. Okay, please remember this thing also. So this RB creates anti-clockwise movement towards RA. So minus RB into perpendicular distance is L. Then this W creates clockwise movement towards A point. So plus W into L, because of we have to convert UDL to point load. And then it will act at L by 2, which is equal to 0. So now we will shift this RB into L to right side. So WL into L by 2, which is equal to RB into L. So this L and this L gets cancelled. So what is remaining? RB, which is equal to, yes, RB, which is equal to
WL by 2.
Yes, good. So therefore RB, which is equal to WL, RB, which is equal to WL divided by 2. So this is the value of RB. Now we will put this RB value in equation 1 and we will find out the value of RA. So put RB in equation 1. In equation 1. So what is our equation 1? RA plus RB, which is equal to W into L. So RA plus WL by 2, which is equal to WL. Therefore, RA, which is equal to WL minus, because of this plus, when we will shift to right side, minus. So WL by 2. So therefore, RA, which is equal to, okay, here denominator 1 and here 2. So first we have to make same denominator. So 2WL, we will take cross multiplication. 2WL minus WL divided by 2. Therefore, RA, which is equal to, okay, 2 minus 1. So 1WL divided by 2. So RA, which is equal to WL by 2. So these are the values of RA and RB. So RA is WL by 2 and RB also WL by 2. Once we get the value of RA and RB, now we are eligible to find out or able to find out shear force at various points. So we will do shear force calculations. Okay. So next step is our step number 2, shear force calculations. Step number 2, shear force calculations. Shear force calculations. So first we have to find out shear force at A. Shear force at A. So now you observe figure and tell me shear force at A, which is equal to how much? Shear force at A, which is equal to. Okay, you observe here at A point only one force is applied. Okay, and whenever we will do shear force calculations at that time, clockwise rotation is positive and anti-clockwise rotation is negative. So this RA creates clockwise rotation. Okay, so shear force at A, which is equal to shear force at A, which is equal to only RA. So value of RA is W by 2 kilonewton. W by 2 kilonewton. Okay, sorry, WL by 2 kilonewton. Value of RA is WL by 2 kilonewton. Okay, after that, next we will find out shear force at X from A point. We will find shear force at X distance from A point. From A point. Okay, so from this A point, we will take section at X distance. So our figure is likewise. Okay, our figure is likewise for this particular case. Okay, we have taken here suppose section and this distance is X and this is RA. So RA value is WL divided by 2 and here UDL is applied and the intensity of uniformly distributed load is W kilonewton per meter. So for this particular case, we have to find out shear force. Okay, so therefore shear force which is equal to so this RA creates clockwise rotation, so it will be positive, so WL by 2 and this W creates anti-clockwise rotation, so minus W into perpendicular distance. Why I have taken here distance? Because of this UDL is given na, so we have to convert into point load, so WX. So shear force at X distance from A point, which is equal to WL by 2 minus W into X. So next step, third step, we will find out, third, shear force at B, shear force at B before RB, before reaction. That means without considering this RB value, we will find out shear force. Okay, so we will consider this whole figure. Okay, we will consider this whole figure without this RB. Okay, so here W kilonewton per meter and this is RA, which is equal to WL by 2. So we will consider all these loads. So, and this distance is L meter. We are finding out at B, but without considering this reaction. So this RA creates clockwise. Okay, this RA creates clockwise. So shear force which is equal to WL by 2 minus W into L. Perpendicular distance is W into L. Again here we have to make same denominator. So shear force which is equal to WL minus 2WL divided by 2. So which is equal to shear force which is equal to plus WL by 2 or minus WL by 2?
Minus WL by 2.
Yes, minus WL by 2. So shear force at B before reaction which is equal to WL by 2 kilonewton. last shear force calculation is remaining, shear force at B point after reaction. Shear force at B after okay after B. So we will calculate. Next is shear force at B after reaction. After reaction. So that means we have to consider whole figure. We have to consider this whole figure. Okay. This unity, this is W kilonewton per meter. This distance is L. This is WL by 2 and this is WL by 2. So we have to consider here all forces. Okay. So here so shear force at B, which is equal to after reaction. Okay, shear force at B after reaction, which is equal to plus WL by 2 minus WL. Okay, and then plus WL by 2. Okay, so therefore shear force which is equal to, okay, so first we will solve this and then we will solve this. Okay, so here one denominator is there. So WL minus 2WL divided by 2 plus WL divided by 2. So shear force which is equal to minus WL by 2 plus WL by 2. So which is equal to 0 kilonewton at B point. Shear force at B point is 0 kilonewton. Shear force at B point is 0 kilonewton. And then we will find out shear force at C. Shear force at C. Last is shear force at C, which is equal to shear force at C. So that means here we will consider C point at X, which is equal to L by 2. So we will consider C point at central point. Okay, C point is at central point. So which is equal to, so shear force at C, which is equal to, for this only that much load, WL by 2, and here UDL is applied, W, and this span is L by 2. Okay, so shear force at C, this is plus WL divided by 2, and this anti-clockwise, so minus WL by 2, because of W is the uniformly distributed load, and we have to multiply by this span, so WL by 2. So therefore shear force at C, which is equal to 0. Shear force at C, which is equal to 0 kilonewton. So these are the calculations for shear force. Okay, then we will find out, or we will do calculations for bending moment. We will do calculations for bending moment. Okay, so please, next step is bending moment calculations. Step number 3. Step number 3 is bending moment calculations. Bending moment calculations. So for this, once again, I will draw figure here. So this is our span, and here uniformly distributed load is applied, W kilonewton per meter. This is A point, this is B point, and this is L. So here WL by 2 and here also WL by 2. So now we will do bending moment calculations. So we will calculate from B point. So bending moment at B. First is bending moment at B. Bending moment at B, which is equal to. Now you tell me, at bending at B point, one force is applied. Okay, so whenever we will do bending moment calculation, sagging positive, hugging negative. So upward force creates positive energy. So this upward, so it will plus WL by 2. But perpendicular distance is 0 because of here this load is at in that particular point, so which is equal to 0 kilonewton meter. Okay, 0 kilonewton meter. Second, we will find out bending moment at x meter from B. Bending moment at x from B point. X from B point. X from B point. So we will find here bending moment at x meter from B point. Okay. So this is our figure. Here WL by 2 force is applied and we have taken section here. Okay. And here the uniformly distributed load is applied W kilonewton per meter. Now perpendicular distance is x meter because of we have taken section at x. So now we will calculate bending moment here. So bending moment which is equal to bending moment which is equal to. So this WL by 2 creates sagging moment. So plus WL by 2 into perpendicular distance is x meter because of we have taken section at x meter. So WL by 2 into x minus. Now this uniformly distributed load, first we have to convert into point load. So W into X, W into X, and then it will act at its CG, so X by 2. Okay, so now we will solve. So bending moment which is equal to, okay, bending moment which is equal to WLX divided by 2 minus WX square by 2. WX square by 2. So you observe here, x raised to power is how much? X raised to power is here 2. So this 2 means x raised to power, this 2 means diagram is parabolic. Diagram is parabolic connection. So whenever we will draw bending moment diagram, so you have to remember x raised to power is 2. At that time we have to draw bending moment diagram as a parabolic connection. Okay, after that next we will find out bending moment at B point, sorry, bending moment at A point. Bending moment at A point. So next is bending moment at A. Bending moment at A. So for this whole beam we have to consider. So this is WL by 2. This is WL by 2. And here uniformly distributed load is applied W kilonewton per meter and this span is L meter. So this WL creates sagging moment. Okay, this WL creates sagging moment. So bending moment at A which is equal to this WL creates sagging. So plus WL divided by 2 into perpendicular distance is L. Okay. Then this W creates hugging moment, hugging type of moment. So we will consider minus W into L. This is uniformly distributed to point load and it will act L by 2. So therefore bending moment at A point, WL square by 2 and WL square by 2. So plus WL square by 2 minus WL square by 2 which is equal to 0 kilonewton meter. So bending moment at A which is equal to 0. And last we will calculate bending moment at C point. bending moment at C. That is x, which is equal to L by 2. That means we will find out at central. Okay, we will find out at central. So suppose this is our B point, WL divided by 2. Here uniformly distributed load applied, W kilonewton per meter, span is L by 2, and here we have taken section. Okay, so this WL by 2 is creates sagging movement. So bending moment at C, which is equal to plus WL by 2 into perpendicular distance is L by 2. Okay, and this W creates hugging moment, so minus WL by 2 into WL by 2 into it acts at center of this L by 2. Okay, center of this L by 2, so L by 4. Therefore, bending moment at C, which is equal to WL square by 4. This is WL square by 4 minus WL square by 8. WL square by 8. So we have to make same denominator. So which is equal to 8WL square, or we will multiply here by 2 into 2. So okay, we will multiply by here 2. So 2WL square minus divided by 8 minus WL square by 8. So now you tell me bending moment at C, which is equal to 2WL square minus WL square.
WL square.
WL square divided by 8 kilonewton meter. So these are the bending moment calculations. Now last part is remaining. We have to draw bending moment diagram and shear force diagram. So now we will draw shear force and bending moment diagram here. First I will draw original beam, and then we will draw shear force diagram and bending moment diagram. So this is our simply supported beam and uniformly distributed load is applied throughout the span. After that, we will extend all these lines. So we will draw shear force diagram and bending moment diagram very effectively. This is central point C. Okay. So this is our A point. This is B point, and on that AB span, one uniformly distributed load is applied, W kilonewton per meter, and span is L meter. Span is L meter. So for this, we have to draw shear force diagram. So shear force at A point, which is equal to how much? Shear force at A point. Yes. Shear force at A. Okay, you observe here. Shear force at A point, which is equal to
Plus
WL by 2.
WL by 2. So plus, that means this point will comes above baseline. Okay, above baseline. After that, shear force at B before reaction. Shear force at B before reaction is minus WL by 2. Minus WL by 2. So that means it will goes downward. Okay, suppose here this point is there. Suppose this point is here, minus WL by 2. So it will go downward. Okay, and after that, shear force at B, which is equal to 0. Shear force at B, which is equal to 0 kilonewton. Here 0 kilonewton, and here plus WL by 2. And shear force at C, which is equal to, shear force at C, which is equal to
0 kilonewton.
0 kilonewton. So this is our C point. This is C point. And here shear force at C, which is equal to 0 kilonewton. Okay. So now we will connect figure. From this point 0, and after that it goes downward minus, and then here 0. So this is our shear force diagram. Okay, so this diagram is in positive and this is in negative. So this is shear force diagram. Okay, then next we will draw bending moment diagram. So bending moment calculations are available here. Okay, so first I will draw baseline. Okay, this is our baseline. So bending moment at A point. Bending moment at A point is, okay, you observe here, bending moment at A is 0. So here 0. Then bending moment at X distance, we have, okay, bending moment at A point is 0. Bending moment at B is again 0. So here bending moment is 0. After that, next, now you observe here, bending moment at X distance. We have calculated this for connection. So x raised to power 2. So this 2 indicates our bending moment diagram is in parabolic nature. Is in parabolic nature. After that, next, bending moment at C, which is equal to WL square by 8. So at C point, we got maximum bending moment, and the value of maximum bending moment is WL square by 8. So this is our maximum bending moment, WL square divided by 8, and whole diagram is in positive. So this is bending moment diagram. Okay. So from these all from this SFD and BMD, you have to remember, if simply supported beam and uniformly distributed load is applied throughout the span, at that time shear force which is equal to WL by 2 and bending moment which is equal to WL square by 2. One MCQ will be asked on this figure. So please you remember, if simply supported beam is given and uniformly distributed load is applied throughout the span, at that time shear force which is equal to WL by 2 and bending moment, maximum bending moment which is equal to WL square by 2. And this parabolic nature, why we have drawn? Because of x power is 2. That's why we have drawn here parabolic. X power is 2. So parabolic nature. So parabolic nature. And here you observe here, we have calculated shear force at X distance. Okay, shear force at X distance. So here x raised to power is 1. X raised to power is 1. That's why here shear force diagram is straight line. So you also write here, x power is 1. So inclined straight line. Inclined straight line. You have to remember that. Inclined straight line. Okay. So please write down. Anybody having any doubt, ask me. Otherwise, please write down. So this is our first slide.
ma'am.
Okay, have you written this also?
5 minutes.
Okay, please write. Okay, Ohar,
No, ma'am.
yes?
1 minute.
Okay, okay, let me know.
Oh, ma'am.
Okay. So next we will take simply supported beam with uniformly varying load. Okay, with uniformly varying load. So SFD and bending moment diagram for simply supported beam, with uniformly varying load. Uniformly varying load. Okay, uniformly varying load. So for this, I will draw figure. You can also draw. So this is our simply supported beam. Okay, and here uniformly varying load is applied. So this is AB span, AB beam, and span for this AB beam is L meter. L meter. Okay. And this intensity of uniformly varying load is W. Uniformly varying load is W. And this is RA and RB. So now you try to calculate RA and RB. Okay. You try to calculate the value of RA and RB and give me answer in next lecture. Okay. This only you calculate reactions. Calculate reactions. Okay. Then we will continue how to calculate shear forces and bending moments in next lecture. So homework for you, that is calculate reactions only. Calculate reactions. Okay.